Welcome to Heat Transfer. Today what we are going to talk about is what is heat transfer, its relation to thermodynamics, different forms of transport phenomena, and three modes of heat transfer. So let's start by what is heat transfer. So heat transfer, in simple word, what we refer to is the exchange of energy or flow of heat due to a temperature difference. Now, when two bodies at different temperatures come in contact, now we expect to see the exchange of energy or the flow of heat from a body with the at a higher temperature to the body at a lower temperature. And this is what we refer as a heat transfer. Now, when we talk about this exchange of energy, it reminds us of thermodynamics and the processes that we have seen here. So it's good to look at the relationship or the differences between thermodynamics and heat transfer. To start for the thermodynamics, I would like to go over the first law of thermodynamics, and I'm sure all of you guys are remembering that one. The first law of thermodynamics, which gives us conservation of energy. Now, conservation of energy, we can write it in a simple word as energy in for any system minus energy out plus energy generation minus consumption is going to be equal to accumulation. And this conservation can be right for any entity for a system. We can write it for an open system or for a closed system. In closed system, we don't have exchange of mass. We are dealing with a constant mass. But in an open system, we can have mass crossing the boundaries. Now, for writing for an open system, I would like to draw the control volume. First, I would have the reference frame, which is at z equal to 0. And what I'm gonna do, I'm gonna draw a control volume where I one inlet and outlet. So this is the control volume that we have. A mass rate m dot can get in with the internal energy of U pressure times specific volume and velocity of I. I'm just putting I as an inlet. I'm going to put a little bit of notation. What's the U? U is internal energy. P is pressure. V is specific volume. V is pressure, and small v, and capital V is velocity. The same thing we can have for the outlet. I'm just going to put it with the different color, that we can have some mass and some mass taking out energy from system with the internal energy, pressure, specific volume, and certain velocity of out. We can have exchange of heat to the system. So we can put some Q here and can get some work out of the system, which I'm putting as a W dot here. If, or I'm just gonna specify that as W dot S. The first law of thermodynamics, or this conservation of energy, I can just write it down in a rate basis. If I write the conservation generate. What we have here is we are giving some energy in the form of heat here, Q, plus I'm just specifying one form of inlet for energy, but it could have multiple of that. So I can have this summation of m dot internal energy, pressure specific volume, plus the form of kinetic energy and GZI. This one is going to be equal to whatever energy that is taking out of the system, which are sigma m dot u plus specific energy. In fact, I'm just going to put the notation I here, plus 1/2 square gz out plus w dot s. Now, I missed adding one point here, which is the elevation.
I can learn to understand you much better if I can get familiar with the way you talk.
Excuse me. So if I put the elevations here, this is gonna be Zi. Inlet and outlet could be at a different sort of elevation for this control volume. And this is gonna be Zo. Okay. And this Q, this is gonna be heat rate into the system. And WS will be shaft work. Now, U plus P small v, this is H or enthalpy. This one is kinetic energy. This one is potential energy. The same thing here. H, kinetic energy, and potential energy. And this is equation 1.12d in your textbook. So I would recommend you to go over that. It provides a good overview of the open system, closed system, and thermodynamics for this one. Now, one thing that we're gonna note here is in most engineering problems dealing with the heat transfer, kinetic energy, potential energy, and the work terms are much smaller in magnitude. So I'm just gonna write it down. So we can essentially neglect them. So in most therefore, we can simplify the above conservation of energy as Q Of course, this can be exact for certain processes when there is no work or kinetic energy or potential energy. And the way that we are looking, this is a conservation of energy. And that's what we call macroscopic treatment. And what do I mean by this macroscopic treatment is it doesn't give us much details about what happens. It tells us about the change of the energy or change of this control volume from one state to another state, but doesn't give us much details. Let me bring an example here. So as an example, let's say we have a iron bar at the high temperature. So this is the oil at the lower temperature. I'm just gonna, let's say, put T2. Let's assume this is 20 degrees C, just an assumption. And let's say we have an iron bar that we are gonna cool it down in a process. Okay, so this is the iron bar, and let's say we have this iron bar at another temperature. I'm gonna put a T1. Let's assume 1000 degrees C. Okay, so the process of when we're pulling this ingot of iron in an oil bath, okay, in an oil bath, we can write down from the conservation of energy that the change in the internal energy, delta U, is gonna be mc delta T. And you guys are familiar with that, where C is specific heat, and delta U is the change in the internal energy. The equations that we have here is the energy balance equation. So we have energy balance equation without phase change, and so far we haven't dealt with time or anything. It doesn't tell us anything about time. It doesn't tell us about like how the temperature profile will look like inside the iron bar. Like from the outer side, I assume the outer side will first get cooled down, and then the cooling will just get into everywhere into this iron bar. So in another word, thermodynamics does not So, simple words, thermodynamics does not tell us anything about how fast, how slow a process can take place. However, that's the requirement in many engineering process. Like, let's say, for example, in this process of like cooling down of this iron bar, we really need to know like the time is very important. The temperature distribution is very important. So, in most engineering problem, we need to know how fast the cooling or heating process happens, or what's the temperature distribution. And that's what we refer here as a microscopic treatment. Of course, that could involve many other things, but for the sake of our discussions here, this is what what we are looking for, or what we are referring as a microscopic treatment, as opposed to the macroscopic treatment that we could get from the thermodynamics. I can summarize what we have been discussing here as just gonna put this one in a little box here. So this is essentially the focus of this course. Heat transfer deals with the rate of energy that flows between different media, how temperature will vary in time and state, okay? And thermodynamics essentially deal with the equilibrium state, when we reach to the equilibrium, but heat transfer deals with the rate, or deals with time, with the time of energy exchange. Next, we will discuss about the different transport phenomena that can happen.